All right, so yesterday we started talking about all things matter and atoms related. So we know there are four major elements that are required for all life, at least life as we know it. I mean, if we're, some sort of weird alien, this might not be true, but for life as we know it, there are four major elements that we need: nitrogen, oxygen, hydrogen, and carbon. All right, I'm going to mute everybody. You can unmute yourself if you have a question, but there's some sort of weird background noise. There we go. All right, so we went over, this is the periodic table. I am not going to have you reproduce this. This is just informational. Here were our major elements. Oxygen, which is required for energy. Every single little tiny cell in your body needs oxygen. Carbon, we are carbon-based beings, and in fact, a lot of the nutrients that we take in are also carbon-based. Things like fats and fatty acids have carbon backbones, and that's going to be for our organic molecules. Also, proteins and carbohydrates. Hydrogen, this is going to be needed for energy transfer, and then, of course, nitrogen is a component of our proteins. In fact, that's where we get our nitrogen, is primarily from like skeletal tissue. When we're eating animal tissues, we're taking in about 16% nitrogen. And it's necessary for things like nucleic acid, which is a major component of our DNA. Here were our minor elements. We went over kind of the basics behind these. Calcium and phosphorus, BFF, 1-to-1 ratio. Potassium is really important for nerve function. And in fact, it's potassium and sodium that help to transmit nerve impulses. Those of you that have taken anatomy in the past know the sodium-potassium pump. We're going to go over the sodium-potassium pump, but not until way later. Way later, don't worry about it. Sulfur, chlorine, magnesium. And then we went over our minor elements. There we go. Oh gosh, what did I just do? There we go. There's our trace elements. Trace elements are what we need in very, very small amounts nutritionally. It's not so much referencing how much we have in our bodies, because things like iron, we actually have quite a bit of iron in our bodies. This is more referring to what do we need to get from our environment. And the big ones that we're going to be talking about, not so much right now, but later on when we get to nutrition, are like iron, copper, zinc, selenium, iodine. Those are all inorganic nutrients that we need in our diets, but we only need them in very small amounts. This is one of the things I love about working from home, is I can drink my Diet Coke while I am teaching. All right, we started talking about atoms. We started talking about all the components of the atoms. We know that an atom must have three components: the protons, which have a positive charge, the neutrons, which have a neutral charge. Protons and neutrons are found in the nucleus. And then we have our electrons, which have a negative charge. And they're like the Noceum cloud around the outside of the nucleus. Protons and neutrons determine the weight. Oh, that's important. You might want to put a little star beside that. That sounds like a wonderful test question. Which of the following components of the atom contribute to the atomic weight? Bam. There, we just wrote our first test question together. Electrons, as I said, they orb. So it's not a planetary orbit. It's not like the Earth around the sun. It's more like the cloud of bugs. What was it you called them? The gnats. We call them noceums. And this cloud of bugs, and some more bugs over here than over here. And what that does is that can actually change the charge of the atom more on one side than the other without changing the number of electrons. So there's our picture, Big Bang Theory. The number of protons gives us our number. So protons and neutrons together give us our weight. Electrons do not contribute to the weight because they don't really weigh anything. The number of protons alone gives us our atomic number. Now, if we gain or lose an electron, this is what we now refer to as an ion. Ion is simply the term for we have gained or lost an electron. If I gain an electron, I become more negative. If I lose an electron, I become more positive. And if I have a negative or positive charge, I can electrostatically be attracted to the opposite, and that would then be the ionic bond. If I have
really bad.
Am I don't know what to do about that because it says that my internet, it says that my internet is full.
So on
I'll
our
do like one sentence and then it cuts
go
out.
between red and yellow connection.
What was that, Joseph?
So in the bottom left of your screen that I'm looking at, it's the connection is showing red bars and then yellow bars, and then that's when you start to lag really bad.
I don't know, because on mine I have full bars. I don't know.
Well, you just did it
Here.
again.
Let me see if I can connect to my hotspot and see if that will help.
She has a real bad connection, so she's probably not getting nothing.
What was that?
I said Latrice already, like when she has to Zoom, she already has difficulty with her connection too. So I can imagine that she's probably not getting nothing of what you're saying.
Yeah, she
Right?
typed in the chat and said, "Is it me, y'all? I can't hear anything."
Okay.
You and her both have bad connection.
That is just bizarre because mine, I'm going to pause this. If we lose an electron, we become more positive. If we gain an electron, we become more negative. Opposites attract. So if I have an atom that is a little bit more negative, a little bit more positive, these are going to be attracted together by electrostatic. Now, if I have an atom with a different number of neutrons, because neutrons and protons found in the nucleus, they should be found in the same number. But if we have a different number of those, then those are referred to as isotopes. I know these are a lot of weird words, but right now we're just now talking about the just definitions, essentially. These are just, that's the depth we're going to go, is just defining the terms. There we had our pictures. There's our 4 major elements. Here's the innermost shell. The innermost shell wants to have 2 electrons in it. And then as we go outer shells, they're going to have 8. And excuse me, these electrons are looking to satisfy themselves. So they want that outermost shell to be full. Whether that means picking up an electron, dumping an electron, or sharing an electron, any of those will work as long as that outer shell has been satisfied. We talked a little bit about how we have these isotopes. So we have a different number of protons than neutrons. And that gives us same element. Like, for example, here we've got carbon, same element, but we have different variations. And we talked a little bit yesterday about the rate of decay. Oops, I went too far. And how we can use our knowledge of specifically carbon, and we can see how has it decayed. And that'll kind of give us a clue as to how old something is, because we know how long it takes. And so we can get that fossil, and we can be like, okay, well, this is 30 million years old. Well, how did we figure that out? We're not just guessing. We're looking at the carbon dating. We're looking at how did that carbon decay. And depending on the form, the variation of carbon, then that will have variations as far as how quickly is it decaying. Here we have our ion. Here we have sodium. Let me get my, let's go ahead and get this fancy. There we go. So here we have sodium. And you can see here in the outermost shell, We've got one little electron. Now, it's way easier for us to get rid of that one than to try and pick up 7. And we always want to use, you know, the method that's going to take the least amount of energy. So it's going to be a lot easier for us to just kind of flick that electron off. That's going to give sodium a slightly positive charge, right? If electrons are negative and I get rid of something negative, I become positive or more positive. Oops, come on, let's turn. There we go. Here's that rate of decay we were just talking about, specifically in reference to our carbon. We're just looking at the disintegration and how long did it take. So it's the variation carbon-14. I'm not going to test you over that. It's just I found it kind of interesting that we can, you know, use our knowledge of how these elements start to decay and degrade, and use that to, you know, age dinosaur bones and fossils and stuff. All right, so our electron shell. In the innermost shell, we want to have 2. Outermost, outermost, outermost concurrent shells all want to have 8. And we're really not going to go much further beyond that. Electrons or shells that are full are going to have less energy. They're not going to be as active. They're not seeking anything out. We have 2 elements that are what we call inert. And these 2 elements, let's see if I can get my chat going. These 2 elements that already have a full electron shell are going to be helium and neon. And that's another good test question. Put a little note beside that. Which of the following would be considered chemically inert? And that would be helium and neon. Their outermost shell is already full, and so they are not really needing to go out and look for anything. I have too many things open. See, at home I have double screens, so it's much nicer because I have everything open. I have all of the things open. All right, so our first shell contains our 2 electrons, second shell 8. And here you can see helium, the innermost shell has 2. Neon, the outermost shell has 8. So we really have nothing that we need to look for, nothing that we need to accept or get rid of. All right, now we're getting into some new material. Molecules are where we are joining atoms together. We can have what is called molecule of the element. What that means is I have 2 atoms of the same element bonded together. They're bonding, there's a couple of different ways that we can bond these atoms together. We can use electrostatic, like an ionic bond, or we can share. Sharing is caring and caring is covalent. And I'll show you kind of some examples of those here coming up in a minute. But no matter how we're bonding these atoms together, that's what's going to make either our molecule of the element or our compound. And all a compound is, same idea. We got 2 atoms bonded together, but they're 2 atoms of 2 different elements. A mixture is just that. Think about like you have protein powder, you have water, you mix it physically together, that provides a mixture. And we've got a couple of different categories of these mixtures: solutions, colloids, and suspensions. Again, I know you know, this is a lot of material, but really the depth we're going to is just simply terminology. We're really just going and defining these. So when we're mixing stuff together, we have the thing that we're mixing into the thing that we're mixing. So for example, if we have the protein powder and the water is going to be the solvent. It's found in the greater amount. The protein powder is the solute. I mix it in, I stir it up, and I drink it, the mixture. So whatever is found in the higher amount of the 2 is the solvent. And whatever is found in the less amount that you're mixing into is the solute. So again, just terminology, simple definitions. Give you guys a minute. Yeah, that's really frustrating that that internet's kicking out because I just spent $200 getting it fixed. Guess who's going back to Best Buy today, I guess.
What do you mean to get your internet fixed? Was there something broken on
So
your?
it was on my, so my computer was not hooking up to the internet. This is my silver HP, the one that I was using. Well, it would not hook up to the internet at all. And so I was having to use my hotspot even at work, at school. And here it was so frustrating because I would be in the evenings taking my own tests for my own school, and it would just drop the internet halfway through the test. And I'm like, ah. So then it got to a point where I wouldn't even connect to my home Wi-Fi. So I took it in on Wednesday, and there was some driver thing. I said, computer sick, please fix. And they said, that'll be $200, please. And I went, okay. And now apparently it's still dropping the internet. So I don't know what's happening.
If you get Geek Squad, I think it's like a membership. My dad has that because he works with computers all the time, and it's easy and it's not $200 every time. I think it's like
No,
a yearly thing.
Yeah, that's what I got, and it's $200.
Really?
If for the subscription, it's $200.
Oh, okay.
But then they'll fix it for the rest of the year.
Yeah, that's what my dad has.
Yeah, that's what I got. All right, so a solution. Solution, by definition, means that, so we have our solvent and our solute. Here we have our example mineral water, right? Obviously the water is the solvent, the minerals are the solute. But with our solutions, the particles are so tiny that we don't really see them. They don't scatter light, and it's going to be clear. So if I look at this mineral water, I'm not going to see, big chunks of minerals floating around in it. The particles are small enough to where they don't settle out and they don't scatter light. They don't make it look cloudy. That's a solution.
Which is usually like something dissolvable then?
Yeah, well, we say dissolvable, but yes. Now there are some things that are not. Like, for example, if you have salt, okay, you take salt, sodium chloride, you put it in water, you stir, you stir, you stir, you stir, you stir. But what happens after a while if you just let it sit on the counter?
It all sinks to the bottom.
It all sinks to the bottom.
Yeah.
That would not be by definition a solution, because a solution does not settle out.
Okay.
Solution, the particles, so when I'm mentioning the particles, the particles would be the individual salt particles.
Okay.
They're going to settle out. Same thing with sugar. You
That's
get a
what I'm
nice,
saying.
lovely hot cup of tea. You put in the sugar, you stir, you stir, you stir. What happens? It's going to settle to the bottom. That is not a solution.
Okay.
This mineral water that I have right here, I can leave this on the counter all day long. Is anything going to settle to the bottom?
No.
It is not. That's the definition of a solution.
Okay.
It is not cloudy. We cannot see the particles, and they do not settle out.
So like
Gotcha.
Kool-Aid, when you pour the Kool-Aid into the water,
It won't settle. It dissolves
it won't
in.
settle because it makes it.
The Kool-Aid won't, but the sugar will.
Yeah.
So the Kool-Aid, with Kool-Aid itself is the solution. The sugar added would be the solute.
The Kool-Aid would be the solvent,
Okay, and the sugar.
and the
would be
sugar would
solute.
be the solute.
Oh my God! I figured it out.
You did figure it out.
I
And
understood
then-
this.
If it does not settle out or look cloudy, that is the definition of a solution.
Gotcha.
Now, colloid. These are really interesting. I actually just did a my assignment last night for one of my classes, I was discussing a colloid. What a colloid is, we still have our solvent, we still have our solute. We are mixing something into something else, okay? That's across the board. These definitions as far as solution, colloid, and suspension, exact same thing. I'm mixing something into something, but these three definitions are simply stating what happens after that. How does this thing act? How does it react?
Chemical reaction here?
Not really chemical reaction, but just what does it look like? How do we
The
use
characteristics.
it? The
of each one.
characteristics, yes, the characteristics.
Okay.
So what a colloid is where we have larger solute. Remember, solute is what we're mixing in.
Okay.
So we have the larger solutes, but they're not settling out.
So it
And
should be like
the other property is they can transform from liquid to solid. Jello. What? Jello is a perfect example of a colloid. So we mix the Jello into the water, solute, solvent. The particles don't settle out. They are larger though. And when we put it in the fridge, it transforms from liquid to solid. And then when I take it to the picnic and leave it in the sun, it transforms back from solid to liquid.
Mm-hmm.
Why is this important? How am I using Jello medically? Here's the really fascinating thing about colloids. We use them as a form of intravenous IV therapy. So I was just doing my paper last night. Actually, I was doing a PowerPoint on parvovirus. And parvovirus can make the blood pressure drop very, very dramatically because of simply the loss of blood. They're like bleeding, vomiting, diarrhea, blood everywhere. We can use a colloid, which is a fluid with large particles that don't settle out. And these particles, it's actually called a plasma expander. And what it does is it helps to increase the pressure on the blood vessels, which helps to regulate the heart. So that's kind of how we can relate all of this stuff to what you guys are doing when you get out into practice. So you are going to be talking, especially, oh my gosh, when you get into pharmacology and you start talking about crystalloids versus colloids, IV, oof, so exciting. So amazing. So exciting.
So it makes the veins bigger, like it expands it.
So yeah, it's called a plasma expander, but here's basically what blood pressure is just that. When your heart beats, right? My heart is beating. When your heart beats, it splooshes out a little bolus of blood. And that bolus of blood causes the blood vessels to expand. If you feel your pulse, when it pushes against your finger, that means your heart has contracted.
That's the pulsate.
That's your pulse. But that pressure on the inside of the blood vessels, if it drops too low, the blood won't move through the blood vessels and your heart has to pump much, 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 much harder. I need to get that volume up because I need to get it into a normal range. Now I don't want to get it blown out, but
it's like the body can tell whether it's full in volume or not. So that's the pumping of the how much.
Right. So if I have a lower volume of blood, it's actually the expansion and contraction of the blood vessels that helps to move and kind of push the blood along. And so if the blood is not causing the blood vessels to expand and contract, then it's not moving along, and it's solely dependent on the beating of the heart to move it along. So what I need to do is I need to get the blood pressure up by expanding the volume of blood, and I can give a colloid to do that, and that decreases the work volume on the heart. So you'll learn a lot more about that when
kind of figure that out a little.
You're going to learn a lot more about that when you get into like pharmacology, special topics, canine diseases. For right now, we just need the definition.
I have a quick question. It's just
Okay.
for my definitions. So solvent, it would be what dissolves the solute.
Yeah, the solvent is found in the higher amount. Solute is what you're mixing into it.
Okay, and solution, is that a mixture of both?
Yes.
Okay, thank you.
Miss Hoff?
So a solution is the first thing the first mixture that we're talking about. Solution, I've mixed something into something. The particles are small and do not settle out. A colloid, I have mixed something into something. The particles do not settle out, but it can transform from liquid to solid.
Miss Hoff?
Yes.
Isn't milk a colloid though? Why would it switch from, or how would it switch?
I'm not understanding your question.
So I think she's talking about like when milk spoils, when it goes from a solid liquid to that chunky and it separates.
That's not a colloid. So if milk spoils, what you're looking at there is the curdles. That is a reaction. That is not a colloid.
No, I was always told like in science that it was. So I was wondering if there's like different definitions for
Wouldn't
colloid.
that be like a chemical change?
So for what we need right now is just the definition. So I'm honestly, I honestly have never heard that milk is a colloid.
So it says that milk is a colloid with tiny globs of butterfat suspended throughout the liquid.
Okay, see, I always thought that milk was more of a suspension versus a colloid. But before we get into a debate about whether or not milk is a colloid, it's a moot point because I'm not testing you over the value of milk.
Gotcha.
All I need you to know is the definition of a colloid. That's it. Finally, we have a suspension where the particles are suspended. And so a great example of suspension would be like our blood. We have the fluid part of our blood, which is plasma or serum, depending on if it has clotting factors. And we have cells. And the cells are suspended in the blood. And so the particles are going to be very, very large. They will settle out. So another example would be the sugar in the tea, the salt in the water. That would be a suspension because as I leave it, the particles will settle out, and that's by definition a suspension. I would have to physically mix it back up.
Okay, so like whenever
More
you
like-
go and donate
Or like Italian
plasma-
dressing.
I'm sorry. Whenever you go donate plasma, that process, is that suspension process where they spin it to separate the white blood cells from the red blood cells?
So when you donate plasma, no, they're separating all of the cells and then pumping those back into you.
Okay. So that would any part of that form be considered suspension anywhere in there where they separate all the cells?
So no, okay, so the suspension itself is the blood.
Okay.
Two components together are the suspension. And then I am removing part of the suspension. I'm removing the solute from the solvent and putting those back into you.
All right, I understand that. Just because I'm a plasma donator, so now I understand what's happening.
Yes.
Okay.
Like salad dressing?
Yeah, so salad dressing, if the particles will settle out and you have to physically mix them back up, suspension.
So that's your Italian dressing.
All we've got, you guys are making this far, 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 far too difficult. I have 3 definitions. Solution, don't settle out. The solution is clear. Colloid, they don't settle out, but it can change from liquid to solid. Suspension, the particles will settle out. At the end of the day, that's all you need to know.
Awesome.
The
Cool.
definitions.
I was just doing word recognition. You were using blood or whatever, and I was using something.
Right. No, absolutely. And
Okay,
so when
cool.
you're talking about plasma and blood cells, plasma's the solvent,
Okay.
blood cells are the solute, and we can separate the two. If you're talking about, we can literally go on all day. Talk about salad dressing. It's settled out. It's a suspension.
Cool.
You have to mix it back up. If it's salt water, it settled out. If it settles out, it is a suspension. If it does not settle out, then it is either a solution or a colloid. And if it goes from liquid to solid, then obviously a colloid. Now, a mixture is very simply something that you have to mix. So not a whole lot of rocket science involved with that one. So our mixtures have to be physically mixed. And I have an example here of a suspension, right? This is a cough medicine. We've all had to take cough medicine. A suspension, if you leave it, the particles settle out, hence the term suspension, and I have to physically mix it back up. That's what calls it a mixture.
Gotcha.
And then a compound, we have special pharmacies. That's kind of why I use this picture. We have compounding pharmacies, and what they can do is take two different chemicals and chemically bond them together. So you can take two different types of medication and fuse them together into one dose.
Gotcha.
When we are using this in veterinary medicine, especially for cats, oh my God, it is so hard to give medicine to cats, especially when they don't want you to, because they have a lot of weapons. And so if I have a cat that does not want to have medicine, holy smokes. So now imagine I have a cat that needs 2 or 3 different types of medicine. No, thank you. Just let it, just hope you have a good life, because this isn't going to happen. But what I can do is I can go to a compounding pharmacy, and they can take all of these medications and compound them together and put them into a form that's a little bit easier to give, like maybe a liquid. And that way I'm only having to give one, but the animal's receiving all of the medications that it needs. So that's a compound, when we have different components chemically bonded together. So how do we bond all this stuff together? Well, we've got 3 different types of bonds. We have a covalent bond, we have an ionic bond, we have a hydrogen bond. If you go onto your Moodle this weekend, I have linked a couple of really cool little videos that are also very helpful in explaining the difference between these 3 different types of bonds. I use 3 primary video personalities. I use one guy called Mr. Ford's Classroom. I use Crash Course, which I think you probably have already been introduced to. I love him. Hank is amazing. And then I also use another one called Bozeman's Academy. So I have already watched and vetted these videos, made sure for accuracy and appropriateness. But I have already linked those below the Chapter 2 PowerPoint. So if this weekend you're like, I don't remember a single word she said, you can go on and you can have access to these videos. They're also all available and linked to my own website. But I wanted to kind of make them all in one specific place. So we're just going to talk about these 3 different types of bonds. So the first type of bond is called a covalent bond. And a covalent bond is where the atoms are going to share electrons. And I have this little saying that just for some reason sticks in my head. Sharing is caring and caring is covalent. And that's how I remember that if they're sharing electrons, it's covalent. Sharing is caring, caring is covalent. We can share more than one. We can share 1, which would be a single covalent. We could share 2, double covalent. We could share 3, triple covalent. They could be shared equally or unequally. And what do I mean by this? So if I have the electrons being shared more on one side than the other, that would be unequal. If they're being shared equally on either side, then we have polar versus non-polar. If they're being shared equally, it means that the charge is the same all the way around. That would be non-polar. If we're having it unequal, where we have one charge is a little more negative than the other because we have more electrons gathering to that area, that would be polar. Polar simply means we have a difference in the charges.
So that's something
Non-polar
like-
means that the charges are the same. Do I have any comments, questions, concerns so far? Is everybody okay? May? Okay.
Good.
Wait, so covalent is when it's always when they're sharing, right?
Yep.
Okay. Yeah.
Sharing is caring, caring is covalent. So it's going to always be when they're sharing. So here I have an example of a covalent bond. And this guy, he is H2O. We have 2 hydrogen and 1 oxygen, and that's a water molecule. And we know that hydrogen has 1 electron. And we know that oxygen on the outside has 6. And so what we're going to be doing is we're going to share the electrons. And actually, this picture is incorrect. How about I fix this? Because you guys are all about to get super, because there should be 6 total before we do the bonding. It's missing 2. Now we've corrected it. So
Oh, now it's supposed to have 8.
before we got our hydrogens, and actually, here's what I'm going to do with this. This will be easier. New share. Do with you guys. I'm going to do this. All right, so I have my oxygen. And I've got 1, 2, 3, 4, 5, 6. I have my hydrogen, who's got 1. And I have my hydrogen, who has 1. And so what we're going to do is these hydrogens are going to gravitate towards the oxygen, and they're going to share. And they're going to share. And so now you can see that my oxygen now, by sharing, has the 1, 2, 3, 4, 5, 6, 7, 8 that he required. And my hydrogen has 1, 2. So everybody's able to share the electrons and satisfy themselves. And what this does is, because they're now sharing these electrons, that has now bonded them together. And so that is, by definition, a covalent bond. Sharing is caring, caring is covalent. We're just simply, hey, I need 1, you need 1, let's just share them. And that way we're satisfied and we don't have to do anything else, and we'll just hang out together. Okay. So that's kind of the premise behind, excuse me, our covalent specific to our H2O. Now, when we are looking at this, you can see, let me get this, that we're not, I got to plug in my computer before it dies. Oh my goodness, that's the one thing I forgot to do this morning.
Oh man.
Just came up
It's
with a
Freaky Friday, I guess.
little warning. Hey, your battery's in saver mode. All right, there we go. All right, so we're sharing these electrons. We know that electrons have a negative charge. And so you can see all of the negative electrons are right here, which is going to give this a negative charge. And you can see that there's no electrons here and no electrons here, which means we're going to have a little bit more of a positive charge. All of our electrons, because we're sharing, have gathered in a more one common space. And so when we go and get out of here and go back to our PowerPoint, so now you can see where we have our where's my draw? I have my electrons. Oops, no. My electrons. No, I want to draw my electrons pen. There we go. So I have my electrons gathered here, which gives this the negative, and I have no electrons here. And so that's what this here is denoting. You can see that we got the negative charge here, positive charges here, and that's the covalent bond of our water molecule. Does that make sense to everybody?
Mm-hmm.
Did anybody fall off the bus with the definition of a covalent bond? Caring is sharing, sharing is caring, caring is covalent. We're just sharing electrons, but because we have electrons more gathered in one area than another, the area that the electrons gather is going to be negative because electrons are negative. And the area where we don't have any electrons is going to be positive. So even though it's the same molecule, it's the same structure, we now have polarized it. We have one area that is a different charge than another. How does everyone feel about that?
You said the area where they are not gathered is positive then? So,
Mhm.
okay, just to make sure.
Yeah, because if electrons have a negative charge and I don't got no electrons there, then I don't got a negative charge.
Okay, well, I have a question on the inner, like the inner shell. How it has the two, you said those get negative, but they're not the ones sharing with the hydrogen. So why do they become negative too?
Because the electrons are always negative.
Okay.
Electrons have a charge of negative, and if I gather more electrons in one area, then that area is going to have a more negative charge. All right, the second bonding possibility is ionic bonding. And so we know already by definition what is an ion. An ion is when an atom has gained or lost an electron. When I gain an electron, I become a little bit more negative. If I lose an electron, I become a little bit more positive. What do we know about opposites? They attract. So this is attraction by electrostatic, positive and negative coming together. This is, so let me give you a true world example of an ionic bond. When you pull your clothing out of the dryer and you forgot to put in a dryer sheet, and you've got socks that are stuck to your pants, you've got underwears that are stuck to your shirt, and you pull them apart and you can hear the bonds breaking. That is electrostatic. That is very similar to how our ionic bonds work. What has happened in the dryer, it also happens to us, is when you rub a balloon on your head, you stick it to the wall. How does it stick? Magic.
Or how
No.
does the hair stand up when you?
How does the hair stand up?
Yeah.
When you put the balloon above your head. That is electrostatic. That is simply you supercharging yourself with electrons.
Crazy.
And then we discharge it. So when you scuff your feet across the carpet, because here's the crazy thing. Okay, I'm gonna stop this because here's the really crazy thing. So I find this fascinating because we can compare ourselves to atoms. There are electrons just pinging around, free floating around. Electrons don't have to be part of an atom. And so we have these little negative charged electrons just bip-a-dip-a-do. And I can gather them up and get them excited. And in fact, there are some people who gather them way more efficiently than others. I happen to be one of those people. And so when you are scuffing your feet or you are rubbing the balloon, what you're doing is you have this Gaussian cloud of electrons around you, like right now, this huge cloud of electrons just around you. And what you've done is you've gotten them excited. And then when you rub the balloon on your head, you've now made the balloon a negative charge because it's gathered up and excited all of those electrons. The wall, in comparison, is more positive because it doesn't have the electrons. Boop. I stick the balloon, opposites attract. That's the fundamental property of an ionic bond.
Gotcha.
That's also how, so when you scuff your feet, what you're doing is you're basically scooping up handfuls of electrons and getting them super excited. And then when you touch the positive doorknob, what happens? You discharge. Now that's obviously not a bond, but that's a great example of how you are scooping up and changing your overall charge.
And so that's where we make the electrostatic.
And that's the electrostatic. So when you put the clothes in the dryer sheet, what it is meant to do is to stop the electrons from getting super duper excited. And so when you get this huge cloud of electrons and you get them excited, you rub the balloon has now got, you think of them like tiny little insects, these electrons. And these tiny little insects are now accumulating around the balloon, giving the balloon a negative charge. The wall does not. The wall, in comparison, is a positive charge. Opposites attract. So now I can take the negative balloon to the positive wall, bloop, they attract. That's an ionic bond. That's literally an ionic bond, electrostatic attraction.
Nice.
So kind of cool. Go scoop yourself a couple of electrons. And in fact, in the winter time is when you are most at risk because the air is so dry. And there are days where I cannot touch my computer with my finger because I will discharge so violently, a spark will fly out of my finger.
Is that why when I lived in Nevada, I literally got shocked by everything I touched?
Yes, because you were scooping up all of those free electrons.
Yeah.
And some people, for some reason, I don't know, I think that was Liz that just said that. For some reason, some people scoop them up better than others. And so you're a scooper like me. You're just like scooping up handfuls and hoarding these huge cloud of electrons, and literally everything you touch, you get shocked.
And so because of the fact that we have a generalization built and construct and a form of how our body works, but the fact that we also can be so individual that it can go, that's why it's always changing, because you have your generalization, then you have those that act abnormally, then they got to go and research and understand why is it doing it different than normal.
Yeah, absolutely. And I mean, it doesn't even have to be abnormal. It's not abnormal that me and Liz scoop up more electrons than other people. Right. It's just something that we're prone to. It's just,
you just built different.
Our physiology.
Right.
But I'll tell you what, in the wintertime, my significant other won't even He won't hold my hand. He won't give me a kiss on the cheek
Always shocking him.
because every time
hold
he'll give me a little kiss, and he'll be like, "Son of a gun!" Because I'll shock him every single time.
I just say it's because our attraction is so electrifying.
Yes, my darling. Yes, it is.
You are shocking.